Good morning, and I'm Kelly, and I'm going to present the article entitled A Fundamental Relation Between Supermassive Black Holes and Their Host Galaxies, from Ferrarese and Merritt, published in 2000. In this work, the authors explored the relationship between the supermassive black hole mass and the stellar velocity dispersion of the host galaxy. Actually, this is the first time that this relation is taken into account. But why do we look for correlations between galaxies' properties? In the matter of galaxy formation and evolution, we have numerous questions that are still unanswered. But there are some things that we already know, but there is a lack of information. We already know that galaxies with a spheroidal component, like elliptical galaxies and the bulge of spiral galaxies, have a supermassive black hole in their center. And we know this thanks to demographic studies. And only a small part of these nearby galaxies have an active galactic nuclei, an AGN, which consists in a supermassive black hole that is being fueled by an accretion disk of matter. In this process, matter is falling towards the supermassive black hole and transforming gravitational potential energy into kinetic energy, thermal energy, and luminosity. This process sends out an energetic radiation that can be responsible for a great fraction of the galaxy's luminosity. But we don't know how exactly the presence of the supermassive black hole influences and is influenced by the host galaxy. We also don't know how the supermassive black holes are formed and how they evolve. So, these are the main questions that guide Ferrarese and Merritt's work, and by understanding how the properties of the black hole mass relate to those of their host galaxies, we can hope to learn about the formation and evolution of both. So, as I said before, in this work, the authors investigate the correlation between the stellar velocity dispersion and the black hole mass. And to do that, they are using two samples of galaxies. The sample A that contains published black hole mass estimates and that are very reliable, and a sample B that is mostly formed by galaxies that do not yet have a published estimate of the black hole mass. And because the masses depend linearly on the assumed distance to the host galaxies, the authors make a correction for distance, and the uncertainties in the host galaxy's distance have been incorporated in the errors in the black hole masses. And also they had corrected the sigma measures to a common system, transforming all velocity dispersions to the equivalent of an aperture of 1/8 effective radius. So in the sequence, the authors use the bivariate linear regression routine to find linear correlations between the black hole mass logarithm and both absolute blue luminosity and logarithm of the central velocity dispersion by taking the black hole mass as the dependent variable. The results of the black hole mass regression fits apply to each sample of any galaxies and are summarized here in Table 1 and in the next figure. We can see here that the correlation between the black hole mass and the bulge magnitude is poor for both sample A and sample B. It's apparent from the reduced chi-squared on the fit in Table 1 that, even by restricting the sample to the galaxies with the most accurately determined black hole masses, the intrinsic scatter in the relation between the black hole mass and absolute blue luminosity remains significantly larger than the reported errors. And we can also see this in this figure. Here we have sample A, here we have sample B. For the bulge luminosity and for the velocity dispersion. And here in figure 1b and 1d, we can see the dependence of the black hole mass on the central velocity dispersion of the host galaxy or elliptical bulge. We can see that this correlation is remarkable. The sample A, which shows a larger scatter here in the figure 1A, now defines a linear relation with negligible intrinsic scatter. According to the authors, this difference in correlations between the two samples may be related in large part to errors in the determination of black hole masses in sample B. So, one of the questions is, why should black hole masses be so tightly correlated with bulge velocity dispersions? The authors suggested that there is a fundamental connection between the black hole mass and bulge mass, with sigma as a good predictor of supermassive black hole masses. And actually, there is a relation. The existence of these correlations implies that the supermassive black hole influences the evolution of its host galaxy, as said by Zubova and King in their work published in 2019. And as Cormidis and Ho say, the correlation is important at a practical level because it allows accurate prediction of the black hole mass from an easy-to-make measurement and because it implies that black hole growth and bulge formation are closely linked. So these are the references, and thank you for your attention.
Okay. Thank you.